Welcome everyone. Thank you for joining us today. My name is Brad Kensler. I'm a data scientist at AWS, and in today's webinar, Edge to Cloud, we'll be talking about deep learning at the edge using Deep Lens, a deep learning enabled video camera. So we're going to start off by talking a bit about high-level overview and agenda for the day. So we're going to kick things off with an overview of deep learning. What is deep learning? How does it work from an end-to-end perspective? And then we're going to dive into AWS Deep Lens, and specifically how to deploy a computer vision project on AWS Deep Lens. From there, we'll move on directly into our workshop and our challenges. So our workshop consists of two labs. The first lab, we will create and deploy a face detection project and deploy it to Deep Lens at the edge. In our second lab, we're going to extend upon the work we did in Lab 1, and we're going to build out a pipeline that will allow us to identify and analyze the sentiments of an audience. So to start things off, we're going to give an overview of deep learning. And the best way to understand what deep learning is by considering it in the broader context of artificial intelligence. Generally speaking, artificial intelligence is the field of techniques and methods that we can use to make a machine behave intelligently. Pretty straightforward. There's a subset of these techniques that consist of algorithms that learn to behave intelligently by observing past behavior, so historical observations. This subset of algorithms is what's called machine learning. These are algorithms that look at historical behavior and learn some sort of intelligence from that behavior and leverage that intelligence in the future. Deep learning is a further subset of machine learning that is concerned with a certain class of algorithms called neural networks. And that's largely what we'll be talking about today. So we're going to give an overview of the end-to-end life cycle of deep learning, but this really is applicable to machine learning as well. The first step in any deep learning life cycle is your data. Your data is what comprises the historical observations that we just mentioned. This is what your model is going to learn from. Once you have your data, then you actually have to teach your model. This end-to-end process of your model learning from your data set is called training. Once you've trained your model, once it's learned information from these past historical observations, then you can use that model to make predictions on new unseen observations. And this is what's called inference. So let's take a closer look at each of these three steps of the deep learning lifecycle. Again, the first step is data. Your data is the historical observations that you want your algorithm to observe and learn from. But learn what? This is largely determined by how you annotate your data. An example of this is the common situation of image classification. In image classification, you have a data set of images, and what you want your model to learn is how to classify these images into particular classes. An example of this is cats versus dogs. You have a data set of pictures of cats and dogs, and for each of those images, you have a label, whether or not that image is a cat or it's a dog. But let's say you wanted to do something a bit more advanced, such as object detection. Object detection is the process of not only classifying something in an image, but localizing it within that image by predicting a bounding box. So in this scenario, your annotations and labels will likewise be more complex. Not only will you have classifications for an image, but you'll also have bounding box coordinates. So whatever you want your model to learn, whatever the task may be, you have to have the annotations that correspond to that task. Once you have appropriately annotated data, then you're able to start pre-processing that data for training a neural network with that data set. Once you pre-process your data, then you can do what's called a data split. So what is a data split? Well, this is best explained in terms of model training. So when we train our deep learning and machine learning models, oftentimes what happens is our models have a tendency to do what's called overfitting. And what this means is these neural networks are so powerful that they can essentially learn to memorize a data set. So again, think about the goal of these machine and deep learning models. We want these models to learn from past historical observations some sort of general information that they can then apply to new unseen observations. When our models learn to memorize a data set, that is not particularly valuable, because when that model sees a new observation, well, it will likely not perform well. So while we want our model to learn from a training set, ultimately we want to evaluate it on data that we have not seen before, because that is what our model is going to make predictions on. So for this reason, during training, we do a data split. We take about 80% of our data, and this is what we train the model on. But we hold out a further 20% of the original data, and we validate our model on that data set. This is unseen data that the model has never seen before. So this is how model training works. Once we have annotated and cleaned the data, then we've split it. We can then start training our model on the training set. And we do this over multiple iterations, which we call epochs. And we validate our model on the unseen, held out validation set. Once our model has reached a state where we are comfortable with its metrics on the validation set, then we want to do something known as inference. So inference is the end-to-end process of taking a new observation. In our use case, we're talking about a new image. We're going to pre-process that new image and then pass that through the neural network and get outputs. And then we do something with that predicted output. In the instance shown here, we're taking the input as an image and we're predicting bounding boxes for detected faces within that image. And this is largely what we'll be doing today. Now, a natural question does arise. Where can we do inference? So there are different options available to us. Oftentimes, we train these models in the cloud using very powerful GPUs. And so it's a natural extension to deploy those models to a cloud endpoint for inference purposes. But there are some disadvantages to that. While running inference in the cloud allows you to leverage all of the powerful compute and low latency that cloud endpoints provide, you may sometimes need to run inference on an edge device if you need either lower latency or you need to run inference offline. And so what we'll be doing today with DeepLens is running inference at the edge on DeepLens. So speaking of DeepLens, in this next section, we're going to go ahead and give a broad overview of the DeepLens platform, as well as deploying a project on DeepLens. So we like to consider DeepLens the world's first deep learning enabled developer kit. And the best way to understand DeepLens is to consider it within the broader context of artificial intelligence at Amazon. Amazon has a long, rich history of artificial intelligence. It's in a lot of different use cases across our business. Things such as the recommendation engines that operate in retail sites, or some of the computer vision use cases such as Prime Air, visual search, the Amazon Go stores, and the Kiva robotics in our warehouses. Arguably, one of the more famous or well-known examples of AI at Amazon is Alexa and our Echo product that employs natural language processing and understanding. But at AWS, we have a very specific mission when it comes to artificial intelligence, and that is to democratize it. What does this mean? Democratization of AI. Well, to AWS, this means allowing developers, whether or not you are ML proficient or not, to leverage this technology in an easy and simple way. And so to that end, we have a machine learning stack of services. At the top layer is our application services. These are services such as Amazon Recognition, Amazon Transcribe, Amazon Translate, services that allow developers to leverage our own deep learning and machine learning models for specific use cases. And they're able to leverage these services by making a simple API call. At the bottom of this stack is frameworks and interfaces. So this is the opposite end of the spectrum. This is where the data scientist or the ML proficient developer can get hands-on with all of the most popular deep learning and machine learning frameworks, such as PyTorch, TensorFlow, Apache MXNet, all of these pre-configured and packaged together in our AWS Deep Learning AMI. This in accompaniment with our infrastructure, such as our EC2 CPUs, but more importantly, EC2 GPUs that you would need to leverage to train deep learning models. In the middle of this stack is our platform services. So these are services such as Amazon SageMaker that are designed to help simplify the end-to-end machine learning lifecycle for data scientists by managing the underlying infrastructure and resources for you. So you as a data scientist can simply focus on your data science. Where does DeepLens fit into this overall stack? So DeepLens is an educational platform. It is a platform that was designed to answer the question, how do we get developers with little to no deep learning and computer vision experience hands-on with this technology, literally? Well, the answer was twofold. First, developers need to be able to get started with sample projects. To that end, the DeepLens platform offers a slew of sample projects that developers can utilize to get hands-on building applications around computer vision use cases. These are things such as object detection, face detection, head pose detection. All of these projects are built around pre-trained models that we've trained on our own data sets and are making available to developers to build applications around. So you as a developer don't need to understand necessarily how to train these different models or algorithms, but you can leverage them for your own use cases. Having these pre-trained models and inference code is only one half of the equation. You also need a meaningful way to deploy and implement these computer vision models and workflows as well. This brings us to AWS DeepLens, the device itself. So AWS DeepLens is a mini computer that's running with an Intel Atom processor, a Gen 9 graphics card that accelerates deep learning computation, has an Ubuntu operating system, there's an integrated camera, and essentially it's a platform that allows you to deploy computer vision applications in the form of deep learning models and inference code in an integrated way to the AWS cloud. A couple of the things that I want to point out about AWS DeepLens. One, it has AWS Greengrass pre-configured on the device. Greengrass is an AWS IoT service that manages the deployment of resources to IoT and edge devices. So when we talk about deploying projects later on in this workshop to the DeepLens device, all of this is being powered by AWS Greengrass. Another thing I want to point out is CLDNN. So as I mentioned, AWS DeepLens has an Intel Gen 9 graphics card on the device itself. The CLDNN library allows you to accelerate computation for deep learning models on this graphics card. So part of the process for deploying models onto these devices is optimization of your neural networks to accelerate computation on this specific graphics card. So I've talked a lot about deploying and sample projects, but let's dive a bit deeper into what exactly constitutes a project. So in order to deploy a project, you must first create one, and a project largely consists of two distinct artifacts. One is the model itself. So this is a deep learning model, a neural network that either we or you have trained for a specific use case in AWS. And you create a project by marrying this model artifact with a Lambda function that executes inference. So you create these two artifacts in the AWS cloud and the DeepLens platform. You create this project, and then you can deploy it to the device. So what do these projects typically do once on the device? Well, the Lambda function is fully customizable Python. You can code it to do whatever you'd like. But for all of our sample projects, the workflow is fairly straightforward. Essentially, what this Lambda function does is it uses a Python SDK that's already on the device to start grabbing frames from the deep lens camera itself. So it'll grab a frame, load it into memory as a NumPy array, do pre-processing on that NumPy array, and then it'll process that array through the neural network model associated with the project. Once that model makes predictions on the input, the Lambda function is then going to take that output and then marry it with the input image, depending upon the use case. If the use case is a simple image classification, then the label will be written out onto the original frame. If it's face or object detection, then the object or face detected will have a bounding box drawn over that object in the image. This output image is then streamed locally on the device and viewable in the Deep Lens dashboard. A couple other things that I want to point out in terms of the high view perspective on the AWS Deep Lens architecture. As I mentioned, AWS Greengrass is managing the deployment of resources to the Deep Lens device itself. In terms of your models, Amazon SageMaker can be used to train your own computer vision models for your own use cases, and you can deploy it to your Deep Lens device in an integrated fashion. AWS Lambda is where we create the inference code that we're going to deploy alongside the model artifact itself. So once you actually have the trained model artifact from SageMaker, you're going to have to actually code the inference code that's going to be executed on the Deep Lens device itself. So you create this inference function in AWS Lambda, and you associate it with a model artifact that creates a project, and then you can deploy it down to the device. And there are two types of outputs that we're able to observe coming from these inference lambdas back into the cloud. The first is video output, which we're able to actually view in the dashboard using Kinesis video streams. The second is data in the form of messages that we're publishing to an IoT topic that you can see in your IoT gateway using the IoT topic and MQTT protocol. Now that we've talked a bit about the deep learning end-to-end lifecycle, as well as given a high-level overview of AWS Deep Lens as well as a Deep Lens project, we're now ready to get started and get hands-on with our workshop challenges. In Lab 1 of this workshop, we're going to learn how to create and deploy a face detection project at the edge. And we're going to do this by creating a pre-built project in the AWS Deep Lens console and deploying it to the AWS Deep Lens device. Let's say, take a high-level overview of the architecture behind Lab 1. In the AWS Deep Lens console, we're going to create a project. And again, a project consists of two different artifacts. The first is the actual model. This is the neural network weights that have been trained on a data set to do a specific task. And then the second is the AWS Lambda function. So this is the Lambda function that is going to be executing inference locally. Once this project has been deployed to the AWS Deep Lens device, it'll then be executed locally by Greengrass. And that execution, that inference, is going to be doing a few different things. We already talked a bit about how the inference works for our pre-built sample projects end to end. There's a couple of things that we wanted to point out. Once the Lambda function runs inference on an input, it does two things with the output. The first is we're going to see that Lambda function publishing IoT messages to the AWS IoT console. So we'll be able to see in real time messages coming from the device itself in the IoT console about the objects or faces being detected locally. Second, the detections from the model are going to be written and streamed in a video output, which we will then be able to visualize in the AWS Deep Lens console itself. So we're going to go ahead and actually jump right into the console and walk through this process. All of the instructions for this workshop, both Lab 1 and Lab 2, can be found at the repository here. That's Kensler/DeepLens Edge to Cloud workshop. You should find this information in the description to this webinar as well. But from here on out, I will make a couple of assumptions. First, that you have registered your DeepLens device. And second, that you have created the IAM roles with attached permissions specified in these instructions. So let's get started. So first we're going to go directly to the AWS DeepLens dashboard. Once we're here, we're going to go ahead and create a new project. So as I mentioned, AWS DeepLens as a platform provides you with a number of pre-built projects for you to get started. Again, we want developers to be able to play with this technology without having to actually build these models themselves. So we have a number of pre-built projects here, but today we're going to be looking at face detection. So once we select face detection, we're going to go ahead and create that project. So I'll say face detection, webinar, Brad. Description, detect all faces in your surroundings at the webinar. And then again, we can see an overview of this project template, right? This is very much what we just discussed about the overall flow that this pre-built model and inference Lambda function will be executing locally. Go ahead and create this project. Okay, so here we can see the project has been created, and our next step is to deploy this project down to our DeepLens device. So the project is still creating. So again, when you create a project, there are two artifacts that are being generated for you for pre-built projects. That's the model artifact, but also the associated Lambda function. So our model has been created, and now we will deploy it to our device. So again, I'm assuming that you have already registered your device and updated it, as we have done here. So I'm going to deploy this project to our DeepLens device here, my DeepLens. We're going to review. So this will show us the project we're going to be deploying, as well as the current project already on the device. There's also a note here on costs. One thing that I want to point out in terms of cost that users of Lambda might think, I want to point out that all the Lambda functions that are executing locally on the device do not incur the same charges that Lambda in the cloud does. The costs that are being referred to here are purely in terms of AWS Greengrass and the deployment process for this project. All right, so we've begun deployment. So I want to talk a bit about what's happening behind the scenes as this deployment begins. So we see here that we're waiting for the deploy project workflow to begin. Now, as I mentioned earlier, AWS DeepLens comes pre-configured with AWS Greengrass on the device. And part of the registration process, as you've gone through it, is to upload a certificate that you've downloaded from AWS to the DeepLens device itself. There's a Greengrass process that's running locally on DeepLens, and what that process is doing is it'll use that certificate that you uploaded to communicate to your AWS account. That Greengrass process is then going to continually communicate and ping Greengrass in your AWS account for some action to do. Now, most of the time that action will be nothing, but when you deploy a project, that state what we call a shadow state in the AWS cloud that the local Greengrass process is reading will change. And it will say, start to download these artifacts associated to this particular project. So when we deploy the project, we change that state in the cloud. The local Greengrass process saw that, and it has started to execute the deployment. So this is actually a pull from the Deep Lens device itself, not a push from the cloud. So we can see right now the model artifact is being downloaded from the Greengrass process on the device itself. All right, so our project has successfully deployed. Greengrass has finished downloading the model artifacts from S3 and Lambda, and it has now executed that Lambda function locally in a Greengrass container. So now that we have our project deployed, there's a couple things that we can do. Now, as we saw in our high-level architecture earlier, there are two types of outputs that we're able to visualize for this project. The first are the messages that are coming from the device that are being published to an IoT topic through an MQTT protocol. So we can go ahead and copy the topic associated to the Deep Lens device and then open up their AWS IoT console and view the messages being published to it. Great. So what we can see in real time are the messages that are being published to this topic from the AWS Deep Lens itself. So what we're seeing is a face is being detected, and we're seeing a confidence score associated for that detection. Now, this is face detection, so the only type of object that this model would detect is a face. But if you were to use a model such as the object detection model, then you would have different labels for different detections. And as you could see, every once in a while you'll get messages with nothing in them, and that's because there's nothing in the field of view for the model to detect. Great, so this is great. You can build some logic around the messages that are being pushed, these type of topics, if you'd like. But of course, what we'd like to do is actually visualize this inference in real time. So we're gonna go ahead and do that now. So part of the registration process, you should have downloaded a streaming certificate and followed the instructions for your particular browser and operating system to add that streaming certificate to your keychain or other application for managing such certificates. We've already done so, so we're gonna go ahead and view the stream now. Great, so now we're able to see the actual output of our model happening in real time. So as you can see, going back to some of the messages that we were seeing earlier, what our model's predicting is a confidence score, which we saw in the IoT topic itself, as well as bounding box coordinates. So we're actually going to walk through what this code does in Lab 2. But essentially what you're seeing in real time is the rendering of the outputs of the face detection model, which is again a confidence score and a bounding box coordinates, and those are being drawn onto the input video stream and then streamed to the local file system, which we're then viewing in our browser. Great. So now that we understand how to create and deploy our very own projects using the AWS Deep Lens console and the device itself, we now want to move on to a use case where we extend off of this pre-built project and build an interesting application around it. In this particular case, our application will be to identify and analyze the sentiment of an audience in real time. But before we actually get into extending this project, we're going to take a closer look at how you could actually train your own face detection model using Amazon SageMaker. So Amazon SageMaker is a fully managed platform that's designed to simplify the end-to-end machine learning lifecycle for developers and data scientists alike. The idea is to manage the underlying resources and infrastructures for developers and data scientists so that way you can simply focus on your data science. SageMaker as a platform is largely comprised of distinct services, and we're going to highlight 3 here, and these each comprise the different stages of the machine learning lifecycle. In the first instance, SageMaker simplifies the building and exploration process by providing pre-built notebook instances that allow you to get hands-on with your data quickly, and also provide all of the deep learning and machine learning frameworks pre-installed for you. And so we're actually going to launch a SageMaker notebook instance, and we're going to explore some of the data that we used to train our face detection model. But exploration and building is only the beginning of the machine learning lifecycle. Once you actually want to train your models, you're going to have to requisition high compute resources such as GPU instances, such as P3, and you may have to requisition a cluster of many different machines to train your machine or deep learning model at scale. So all of this underlying resource management can be quite onerous and has nothing really to do with data science. So what SageMaker does is it manages all of this infrastructure for you, so you as a data scientist can focus on things that really matter to you, such as customizing your own training loop or neural network architecture, or optimizing parameters. But to that end, SageMaker also offers an HPO service, which uses Bayesian optimization techniques to optimize hyperparameters for you as well. So again, simplifying the aspects of model training that have nothing to do with data science so you can simply focus on your ML. Finally, we have deployment. So at the end of the machine learning lifecycle, you want to take your trained model and deploy it in some meaningful way. Now, today we've been deploying our models to the edge to run edge inference, and we've talked a bit before about why that's valuable and the trade-offs between that and inference in the cloud. But sometimes you want to run inference in the cloud and have low latency microservices that you can incorporate in larger web applications. To that end, SageMaker allows you to easily deploy models to microservices behind HTTP endpoints, and it'll set up all of these web serving resources for you. So you as a data scientist don't have to focus you don't have to focus on setting up web servers and things like that. You can just focus on training the model, providing inference code, and SageMaker will prop up that endpoint for you. So we're going to go ahead and jump right into SageMaker. I'm navigating towards the SageMaker dashboard. And as I mentioned earlier, we're going to launch a notebook instance. So again, notebook instances are instances that have been launched from the deep learning AMI. So they have all of your favorite deep learning and machine learning frameworks pre-installed. And then on top of that, Jupyter Notebook environment is configured and installed. So when you launch your notebook, you'll open up directly into that environment. So I'm just sort of going through how you would launch a notebook. You can obviously select different instance types to suit your need, attach elastic inference for acceleration if you'd like, your IAM roles, whether you want that to be in a VPC, lifecycle configurations, all the typical bells and whistles. I'm going to go ahead and create that notebook instance. Now this is going to take some time to launch, so I've already launched one ahead of time that we can just jump right into. So you can see we have notebook instances here. I'm going to go ahead and click Open Jupyter. And SageMaker is going to automatically direct us to a Jupyter Notebook instance. So now we're in the Jupyter Notebook console. So this is the Jupyter Notebook server that has been configured by SageMaker in our notebook instance. So I've already gone ahead and pre-cloned the repository for this workshop into this notebook instance. You can do so as well by popping open a terminal from this menu here. I'm going to go ahead into our workshop repository, head to the SageMaker lab, and I'm going to open up the lab notebook. So in this notebook, we're going to overview how one could train a model for face as well as object detection. I want to just talk a bit about Jupyter Notebook for those that may not be familiar. So Jupyter Notebook is a development environment that is really advantageous for exploratory data analysis, experimentation, and reproducibility of experimentation. It's integrated in a notebook fashion with things like Markdown, so you can provide tutorials, commentary for your code. And the way that the code actually works in the notebook is they can be executed on a cell-by-cell basis. So this notebook is sitting on top of a Python kernel, and we can execute blocks of code and get output in real time. So I'm going to go ahead and start executing these cell blocks from top to bottom. So first, I'm just importing the relevant libraries that we're going to need. Next, I'm going to download some artifacts from S3 for this demonstration. Note that these are actually command line commands that we can execute through the Jupyter Notebook through this exclamation mark here. And then we're just going to demonstrate in a very simple way how you can use these Jupyter Notebooks to explore your data. So here I'm going to load one of the images I downloaded into memory, and then I'm going to plot it. This is one of the images that we downloaded from the data set that we're going to train our model on. So you can see in real time I'm plotting this image. So you can see and interactively play around with your data. Now, as we discussed earlier, your data set and the task that you'd like to perform on it is only as good as the labels you have. So for this particular data set, one of the main components to it is obviously bounding box coordinates. So each of these values correspond to a particular face in the picture, and they dictate where the bounding box of that face in the picture is. So if we go ahead and take these bounding box coordinates and actually plot boxes on that input image, we can visualize this for ourselves. So I just took these numbers and labels up here and used OpenCV to plot these rectangles onto the image. So when we train our model, this is what it's trying to do. The model is trying to predict these four numbers, bounding box coordinates, as well as a class. Now in this case, we only have one class, and that's face. But more importantly, the model has to understand when to detect a face and when not. So now that we've seen the utility of this type of environment for exploring and understanding our data, we can go ahead and actually launch a training job using SageMaker. So I'm going to go ahead and grab the session attached to this environment, grab the execution role inputs. So typically when training your model in SageMaker, you would do your pre-processing and all of that in a Jupyter Notebook. This is quite a large data set, so we've already done this and put this in the following S3 bucket. So we're going to go ahead and train our model on that. Now here we're actually defining the SageMaker estimator that we're going to use. So in this particular example, we're using the MXNet deep learning framework, and we're training a single shot detector model. That's a model that has been designed for low latency, which obviously is of great interest when running inference. And so that's the type of architecture we're going to be using. Now, the code that defines the training logic is in this file here, and so we reference it as the first argument to the MXNet estimator. And if you're using something like TensorFlow, PyTorch, this would follow a similar flow. You would create your own training script, and then that would be the entry point for the estimator. Other things that we're passing into the estimator, right? The role, instance count, the instance type. Here, since we're training our model, we'd like to use a P3 2x large model to leverage the GPU compute to accelerate our training time. And then, of course, we're passing in hyperparameters. I'm going to go ahead and define that estimator. And then we're going to go ahead and launch the training job. So the training job, again, it doesn't happen on the notebook instance, right? What SageMaker does is it manages the underlying infrastructure for your training job. So here we define the estimator. We've pointed to the code that we want to execute. We have pointed to the instance count and types that we want that code to execute on. So when we launch a training job by calling fit on the inputs, again, that inputs is an S3 location. What SageMaker does is it starts a training job by spinning up the number and type of requested instances that we selected. It then downloads the containerized training workflow onto the node or nodes, and then it's going to execute that entry point script that we provided. So this is going to take quite some time, but I've already gone ahead and executed this earlier in a separate notebook, so we can get an example of what this is going to look like. So as you notice, we've only trained this model for one epoch. Obviously, you'd have to train this for quite a bit longer to actually get the type of performance you would like for face detection. This is the sort of output that we're getting here. So you can see once the training starts, we're getting different metrics, such as the speed of the training, cross entropy loss for the classification, as well as the smooth L1 loss for the bounding box coordinate regression. And at the very end of the training job, it'll actually tell you the billable seconds. So these are the billable seconds for the lifetime of the training itself, not the spin up or spin down or the downloading of resources. Great. So now we understand how to actually train this type of model using SageMaker. Now, as I mentioned, you'd have to train this model for quite some time to get the type of performance that we would like. So in the rest of this lab, we're not going to use the model we trained here. We're going to use the pre-built model, but it was trained using the same type of workflow. So you could simply recreate this by just extending the number of epochs you'd like to use. So now that we understand SageMaker and how to extend our projects, we're going to talk a bit about building an application around one of these pre-built projects. So I alluded to this earlier, but specifically, we're going to be creating a pipeline and a dashboard that allows for real-time audience sentiment analysis. So the use case here is you have a dashboard that is going to be giving you real-time analysis of how the audience is reacting to whatever it is you're doing. Maybe you're a public speaker or you're a DJ at a festival. Either way, the best way to get a response and understand how well you're doing is to understand how the audience is reacting in real time. So let's take a high-level overview of the architecture behind what we're going to do here. So we already walked through the process of using Amazon SageMaker to train a model on data that you have in S3. But now we're going to create a new project in the AWS Deep Blends console to do the rest of what we want to do here. So again, we're going to create a project consisting of a model. We're going to use the pre-trained model again, but we're going to use a different Lambda function. So again, our Lambda function before just did local inference, published topics, and streamed out a video. But now we're going to want to do something a bit more in depth. So we're going to augment the original Lambda function and then create a new project with that, and then deploy that project to the Deep Blends device. So it's still going to be doing face detection on the edge, but we're going to be doing different things with the faces. So in the past, we were just drawing bounding box coordinates of the faces onto the input images and streaming them. But in this case, we're actually going to be cropping the face images from the feed itself. So we're going to take those bounding box coordinates, use those coordinates to crop the detected faces in the image, and then we're going to upload those faces into S3. Once those faces are in S3, we're going to have another cloud-based Lambda function that will be listening for that bucket, and it's going to process that face crop through Amazon Recognition. So we're going to be using recognition to detect the emotions of the face crops that have been uploaded to this bucket. Once we've done that, we're then going to push and write the emotion scores for these face crops to a Dynamodb table, but also to an Amazon CloudWatch dashboard, which will be able to visualize these scores coming in real time. So before we get hands-on and walk through how to build out this pipeline, I want to point something out in terms of edge inference. So here we're leveraging edge inference on Deep Blends for face detection, but a natural question could be, well, why are we doing this in the first place, right? Couldn't we do face detection in the cloud as well? Well, you could, but if you were to do that, then you would have to be continuously streaming input from the edge device itself, from the local camera at whatever location you're at. This is going to eat up a lot of bandwidth, and not only that, but you're then going to be running recognition on each one of these frames. So by using face detection on the edge, we're effectively leveraging this machine learning model as a gating function. So now we only push things up to AWS once we've actually detected a face, and then we only invoke recognition on the crop of that face itself, rather than the rest of the image. So edge inference here allows us to be more efficient in our bandwidth consumption and our API calls. All right, so now that we understand at a high level how this pipeline is going to work to create this dashboard, let's go ahead and create it. So as I mentioned, we're going to create a new project. This new project is going to consist of the same model we used in the first project. This will be the pre-trained face detection project or model, but we're going to use a different Lambda function. So the first thing we need to do is go ahead and create that Lambda function. So we're not going to create this from scratch. We're going to use a blueprint. Since this Lambda function is going to be executed by Greengrass, we need to use the Greengrass Hello World blueprint that comes with the Greengrass SDK and associated libraries. So we'll call this webinar edge to cloud Brad. We're going to choose an existing role. So we're going to be using the AWS Deep Blends Lambda role. This role should have been created when you registered your Deep Blends device. And in the initial instructions in the repository, there are additional permissions that you should have attached to this role. So if you haven't done so, please make sure you do that. Next, we'll go ahead and create the function. So our first step is going to be to go ahead and copy and paste over the boilerplate code. So in the repository, we have the inference Lambda. In the instructions, it'll take you directly to this, but I already have this open just to copy and paste it. So I'll do so now. And since we have this Lambda function up and open right now, I want to take the opportunity to walk through this code. This code is very, very similar to the default code that we were using earlier, with one main addition, which I'll point out. But basically, as you can see, we're importing standard libraries. AWS CAM is a library that's pre-installed on the device, and that is a library that helps do things such as grab frames from the camera device or from the camera on the device, as well as use the Intel inference runtime that the model is going to run on. So the local display, this is a simple thread class that we're going to use to write the outputs of the model to a file locally for streaming. Here we're defining the IoT topics and establishing the client to communicate to that topic. Again, this is what we saw earlier with the messages coming in. So this is the key difference, right? We're defining a helper function here to push to S3. We're going to want to extract face crops from the input image and push that to S3. One change that you're going to have to make here is you're going to be using your own bucket, obviously. Mine is Deep Lens Edge to Cloud. Yours will be something else. So make sure to go ahead and insert your bucket there. And then we get to the meat of the inference that's being executed locally. So the first few steps consist of loading the model. So we have a model type, SSD, single shot detector, output map. These are the labels. Since we're doing face detection, there's only one, and that's face. We initialize the local display thread. We have a model path for a model artifact. We start publishing messages to the IoT topic. Hey, we're loading our face detection model. Then we use that AWS CAM package that's pre-installed on the device to load the model itself. We specify that we're going to be running inference on the GPU. Detection threshold. So recall that earlier when we were looking at both the IoT messages and the visualization, there were probability or confidence scores for the detections. So obviously you have complete control over what you want your detection threshold to be, to control your false positive rate and what have you. So here we've set that to about 25%. Input height and width. These are the dimensions we need to reshape our input images into to process it with our network. And then we get into our infinite loop that's executing inference. So first we're grabbing frames with this helper function from the AWS CAM package. We're grabbing these frames from the camera. We're then resizing them. And then we are running inference with the model on that resized frame. And then we're parsing the result. So we get these parsed inference results. And we go ahead and iterate through these parsed inference results. The first thing we do is we're going to check to see if that probability is greater than our detection threshold. If it is, great. Next, we actually calculate the true bounding box coordinates. So what the model is going to output for bounding box coordinates will be on a 0 to 1 scale. So we need to calculate the scaling for X and Y to recover the pixel coordinates for the corresponding input image. Great. So we go ahead and do that, and then we crop the image here. So from the original input frame, we go ahead and crop where the detection was, and then we call that push to S3 function that we saw earlier. And then the rest of this loop is actually doing what the original Lambda function did, which is drawing a rectangle around the input image, as well as drawing the text for the confidence score as well. And then writing that output frame with the local display thread. Great, so now we have a deeper understanding of what's actually happening on the device. We're going to go ahead and save this Lambda function. And then once we've saved it, we'll need to publish. Great, so now that we published the Lambda function, we can actually go ahead and create that project. So we're going to create a new project. This time, rather than use a project template, we're going to click create a new blank project. I'm going to call this webinar sentiment analysis. Brad. Description: detect faces of audience for sentiment analysis. Great. So now we have to manually associate the two artifacts for this project. So the first is the model. This is going to be pretty straightforward. We're going to use the default deep lens face detection model. Great. Next, we need to add the function that we just created. So we see here, webinar edge to cloud Brad. We'll go ahead and add that function. Fantastic. Now we can combine the two into this project and create it. So now our project has been created and we're ready to go ahead and deploy it to the device. So we're going to go ahead and do so now. So again, we're going to select our deep lens device. We're going to review. Again, we can see the project that's already on there is the one we deployed earlier. We're going to deploy over that, no problem. And now our deployment workflow begins. Okay, so now that our project has deployed, we can go ahead and view the outputs like we did before. But really what we want to see is that the face crops that our model is detecting on the deep lens device itself are being cropped and then pushed to S3 as we'd like. So I'm going to go ahead and go to S3. I'm going to take a look at the bucket that I created for these faces. You will have created your own bucket as part of the instructions in the repository. And again, this is the same bucket that you manually coded into the Lambda function that was part of the project. Let's go ahead and look at one of these pictures. Great. So this is a not too flattering picture of me sitting here in the studio, but as you can see, what we've got is the model that's running locally on the device. Took a great action shot of me walking through this and has pushed that up to the S3 bucket. But so far, that's all that's happening, right? And we know that that's not enough. We now need to create a Lambda function that is listening to that bucket and is set to trigger on uploads to that bucket. And again, that Lambda function is going to invoke recognition, and it's going to push the outputs from that recognition API call. Again, these are motion scores. That's going to push those to CloudWatch as well as Dynamodb. So first we're going to create the Dynamodb table that we're going to write these records to. I'm going to call it webinar motion table. The partition key is S3 key. And we'll go ahead and create. So you're going to want to remember the name of your table because we're going to reference it in a moment. So we've created the table. Now we need to create the Lambda function that will trigger on the S3 object creation for that bucket. And then we'll write to that table we just created and then push the emotion metrics to CloudWatch. I'm just copying and pasting the table name. So let's go ahead and create this function. So we'll call this function recognize emotion S3, or actually let's say webinar. We're going to select Python 2.7 as our runtime. We're going to choose an existing role. We're going to choose recognize emotions. Again, this was one of the roles that you were told to create in the repository instructions, as well as attach the relevant permissions to it. So we're going to go ahead and create this function. Of course, there's no code, or there's boilerplate code, so we need to copy the code from our repository into the Lambda function. Great. So let's take a brief walkthrough of this Lambda function. It's pretty straightforward. We're establishing recognition in CloudWatch clients. We have helper functions, one to push to CloudWatch, and these are going to be the emotion scores for detected faces. But the other is a detect face helper function. So the API call we're actually going to be invoking for recognition is detect face. Obviously, we don't need recognition to detect the face because we've already done that. But part of what recognition does in this API call is it detects metadata about the face, one of which is emotion and emotion score. So once we invoke that API call, we then grab the face details from the response, and we enumerate through the face details, and we write those face details to Dynamodb. If you do here, you're going to have to replace the table with the table that you created. You're going to have to create that. You're going to have to replace that table with the table you created. In this case, this is webinar. My memory is not working today. Webinar emotion table. You're going to have to replace that table with the table you created. In this case, that is webinar emotion table. And then you're also pushing that metric to CloudWatch. So this is where we're going to be able to visualize the emotion stream in real time. And then, of course, there's the Lambda handler, which is triggering on the S3 trigger. Okay, great. So we've created the Lambda function code. Now we need to add the trigger. So we're going to go ahead and select S3. We need to configure the trigger. We're going to select the bucket. In this case, that is deep lens edge to cloud. Prefix, we're uploading our face crops to faces. So we want to trigger on things under that prefix. Of course, the event type is all object create events. And then the suffix is .jpg. And then we're going to enable the trigger. So we're going to go ahead and add it. Great. So once we've done that, we can go ahead and save the Lambda function. Now, we actually received an error here, and this is because I already have a Lambda function that is monitoring this S3 bucket, so that way we can actually run this demonstration in real time. But if this is the first time you're doing this, you won't run into this error. So again, I already have a Lambda function that's doing this. So we can actually look at the output of the emotion scores that have been detected throughout this webinar. So let's go ahead and go to the CloudWatch dashboard and see how I've been feeling today. So once you go to the CloudWatch dashboard, you're going to want to click on metrics. Then you're going to want to click on string. These are metrics with no dimensions. We're going to select all of the scores. So you can see a number of different things that's going on here. I'm going to title the graph first. So we'll have emotion scores over time. Right, so first you can see that we were recording this for a while. There's this gap. So I actually had this project running on the device since the beginning of the webinar. We then deployed that first project, so that's what this gap is. And then we can see it resuming after we redeployed it. So you can see different emotion scores over time. We can take a closer look at these earlier ones here. So we can see mostly there's calm, so that's good. It means I can calmly deliver a webinar. Not too much anger there, so that's also good as well. Happiness, mostly calm. Maybe a little bit of sadness. It's been a long day, but the point that we're making here is we built this CloudWatch dashboard, and it is displaying to us the emotion scores that we're detecting from face crops that the DeepLens device is pushing up to S3. And of course, you can play around with the different options of the graph itself, such as the period that these statistics are being averaged. I'm going to set it to 1 minute from 5, so you can get different levels of granularity as well. Great, so that concludes the second part of our workshop. Again, what we just demonstrated was how you can take some of these pre-built projects, such as face detection, and leverage these pre-trained models and build cool and interesting applications around them. So you as a developer don't need to understand deep learning or how to train your own CNNs for these use cases, but you can still build applications that leverage that technology in an interesting way on the edge using AWS DeepLens. So in closing, I just want to point out some sources of inspiration that you may find interesting for your own projects. So if you'd like to learn more about the different types of things that can be done using AWS DeepLens, we had a hackathon some time ago. And we had a lot of interesting submissions and entries demonstrating different and unique ways AWS customers were able to use DeepLens. So first place was a really cool application. Basically, it was a deep learning enabled app that used a computer vision model that would read books to children. But I really like the second place model, D. So this was a project that leveraged one of the pre-built object detection models and incorporated it into a game that you could play with a child. So what the D application did was the project would start and a voice would start talking to the child through DeepLens' speaker, and it would ask the child to show DeepLens a picture of something with a wheel. So the child would have a number of laminated object cards in front of them, things like ducks, cows, cars, bicycles, and if the child showed the correct object to DeepLens, the object detection model would detect it, and it would know, oh, this was the correct object, it's a bicycle, or it would detect, hey, the child showed me a cow. And then logic in the project would say this was the wrong answer. So the child would then be prompted, hey, this is not the right answer, keep trying again. The reason why I like this project so much is because, like what we did today, it demonstrates how far you can go in the applications you can build by simply leveraging these pre-built projects. So as a developer, you don't need to know how to create your own object detection models to build cool applications and use cases. leveraging this type of technology. So thank you for joining our webinar today.